So I want to start in our class and really in every class just with sort of an idea for the day, a thought for the day. So this is a quote. So the greatest obstacle to discovery is not ignorance. It is the illusion of knowledge. This hung on the refrigerator of one of the greatest mathematicians I ever got to work with. Now, I will say that this word discovery can do many things, but in particular, in our case, it also is related to learning. What's our great obstacle to learning? And what is this illusion of knowledge? Well, for that, I would say there's really more or less two things. So what are they? Well, the two things that people struggle with is the background is number one. And by background, I want to say a lot of people think they know algebra pretty well. And many people are correct. I don't want to say, no one knows algebra. A lot of people do, but a lot of people think they know algebra but don't know it very well. Or they understand it incorrectly. And then when they go to apply it, it gets applied incorrectly, and you get the wrong answers. So one of your biggest challenges is not just going to be learning new material, it's going to be relearning or fixing things that you've learned in the past. But we can do that. We have enough time, we can get through it. So just be open to the idea of like, maybe I need to relearn things. Or maybe I need to revisit what I thought I knew. Now, the other illusion of knowledge is a little bit harder to write in a pithy way, but, well, let's just say things look so easy. So you look at an instructor or your recitation instructor, you go to help hours, and they write the answers down, and they're so elegant. The pen flows. The problem works itself. Every step is automatic. Everything is obvious. And you think to yourself, well, this calculus stuff is easy. I don't need to put in the time. Because when it comes time for me to do it, surely my pen works just as well. But it doesn't. If you don't put in the time, you'll discover that your pen will not flow. That things will get stuck. And things that seemed obvious when other people did it are certainly not so obvious. Now, that's not to say that you're not capable. I firmly believe that everybody who enrolls in this class, meeting the prerequisites, can pass this class. But you have to put in the work. The reason we make it look easy is we have lots of practice. And we've worked on it. And we're going to try to help you get caught up as fast as we can. But you also will need to put in the time. But you can do it. I believe in you. I believe in you. All right, so that's our thought for the day. Okay, so we begin calculus, day one. What is calculus? Well, I've come to think of calculus as saying we're trying to answer two types of questions. We've developed some tools. Now, the two types of questions that we're trying to answer, the first one is the question, how are things changing? So we want to understand how things change. In particular, relative to another, are things going up, things going down? And you might say, well, why would we care about that? Well, oftentimes by understanding how things change, we can improve something. And in particular, we can make things optimal, optimization. Make things as good as they possibly could be, and know that we are doing that. So that's actually a very important thing, and that's calculus lets us do that. The second question, how much is there? So we have something we're trying to measure. It could be geometrical. area, could be volume, surface area, all sorts of things geometrical, but it could be something, how much money, how much energy. Anytime you want a measurement, that's a question of how much is there. So those are the two questions. Now, why do we study them both in calculus? Well, many years ago, there was a smart person. Of course, there's still smart people left today. And they said, hey, these are connected. And in case you're wondering who said that, that's Isaac Newton. He said, you know what? The tools that we need to answer the question, how are things changing, turn out to be connected to the tools that you need to answer the question, how much is there? And so that's why we study them together. Now, in terms of the course, we're going to spend about the first 2/3 of this semester focusing on the first part. How are things changing? And then the last third, we'll talk about how much is there. Now, don't worry, we have more calculus classes for you to take. So if you're like, I really want to spend more time here, you will get your opportunity. I promise you. I promise you. All right. So let's begin with the change. So we want to understand how things are changing. So when we talk about measuring change, what are we trying to do? And the key word here are rates. We're after rates. And when we talk about a rate of change, understanding how something is changing, you have to remember, it's not something happening in isolation. It's how are things changing relative to each other. So when we talk about speed, speed is an example of rate that we're very familiar with. We've grown accustomed to it. We might talk about like 60 miles per hour. Well, what are we saying? Well, if we say we change 60 miles in a given hour. But of course, if we go, say, a fraction of an hour, 12 minutes, then we say, okay, we go the corresponding fraction of the mileage, so 12 miles. 60 is a very convenient number for these kinds of computations. So more generally, we can think of, well, suppose there's a relationship between two variables, and we like y and x. There's nothing really sacred about these symbols, but by convention. So there's a relationship between y and x. Two things which are changing. So as we change one, the other comes along. And the way we usually write this is to say that y is a function of x. So a function is just another way of saying there's a relationship. So when we're talking about a rate, what we're really after, we're saying, well, how is y changing as, which becomes division, x is changing. So it's sort of this ratio, change in y over change in x. That's roughly what the rate is. And it's good to help us think about, like, okay, is there anything that we're comfortable with where we understand what's going on? Does that formula look familiar? Change in y over change in x? Have you seen it before?
Yes.
Yes, okay, good. Okay, good. Where? The slope. So it's good to start with things that we're somewhat familiar with. So we could say, aha. We'll have many of these great ahas. We think to ourselves, hey, change in y over change in x, that's a slope. Okay, so in particular, we can start with things which are flat. So we have our coordinate systems here. We have our x, our y, and we have our line. And so when we talk about our slope, well, the way you measure slope, you pick 2 points on a line, and you say it's the ratio of change in y over change in x. Now, usually you write this as rise over run, but the moral is it's a slope. So the slope is acting in this case as our rate. Okay, cool. So I do want to pause here and say we like flat things. One of the big underlying ideas in calculus is the world is full of bumpy things. But you know what? When you look close, things look flat. And we like flat things. So it's not surprising that when we oftentimes start by saying, let's understand the flat thing. So for us, we have a line. All right, well, that's good. So if we have a line, life is good. Now, by the way, what happens if you measure your slope at a different point? So say these pair of points versus those pair of points. What happens to your slope? Yeah, it's the same. It's the same. So in essence, everywhere that you look for a line, the slope is the same. Well, but as I mentioned, the world is not full of lines. It has its ups and downs. So functions can do all sorts of things. And now it's not so clear to say, how is something changing? And the reason it's not so clear is because we can clearly see there's differences. You say, well, over here it seems to be going up. And over there, it looks like it's going down. And, it's a roller coaster. Up and down. Okay, so how do we get a handle on it? So a first intermediate step is we're going to say, well, let's look at a simple thing we can do, which is to say, let's pick 2 points, and we'll connect. So what have we done here? We have an A and a B, and then we have, of course, over here is our f of A, over here is our f of B, and then we have what's called a secant line. And a secant line passes through 2 given points. Now, it could pass through additional points as well, but we're saying, look, we're passing through these 2 particular points. It's a secant line. And now we could say, okay, we're going to think about what's going on here. We know what's happening to the function at A. It has this value, f of A. We know what's happening to the function at B. It has this value, f of B. And now we can say, well, the change could vary, but we can look at what's called the average rate of change. Now, the word average here, what do we mean? So average in this context says what rate of change, or in other words, what constant rate of change would produce the same effect. So, in other words, I want to start at A f of A, I want to end at B f of B. What would be the constant rate of change that produces the same effect as the function is currently exhibiting? How do you figure that out? Well, the answer is, we say, look, if I want a constant rate of change, that's the line. And we have our points that we want to go through. So if I want that rate of change, what am I looking for? Slope. The slope of the line. So how do you find that slope of the line? Well, change in y over change in x. What's our change in our y values? F of b minus f of a. What's our change in our x values? B minus a. So that's the average rate of change. If it looks like a slope, that's because it is a slope. So like, yes, I know slopes. Nice. So all right, so that's the average rate of change. All right. Cool. Any questions about average rate of change? All right, well that means then that you're ready to do a problem. And spoiler alert, you're going to do problems. So coming to class means you get to work. But that's good. We should do problems. And the good news is you can talk to your friends. So here's the problem. Find the average rate of change for y equals 4e to the x plus x squared plus pi to the fifth from x equals 0 to x equals 4. All right, so that's the goal. What's the average rate of change for this function? Here we don't give you a picture, we've given you an explicit function. So just to be absolutely clear before we start, this is our f of x. So, okay, all right, so let's talk about it. Now, if you see average rate of change, you sort of start training yourself like, okay, I'm just going to know if I see certain words, I have formulas at my disposal. So average rate of change, we're like, aha, this is like a slope type thing. And so in particular, we're talking about f of b minus f of a over b minus a. That's our slope type equation. What are a and b? Where the x values are. So we can go a equals 0 and b equals 4. It actually doesn't matter which one you make a and which one you make b, because if you switch them, you switch the sign on two things and the signs cancel out. So now we say, okay, we plug in. We're going to talk about f of 4 subtract f of 0 over 4 minus 0. Now, what is f of 4? Oh, I'm going to introduce one of the most powerful tools to help you save points. It's called a parenthesis. So I'm going to put in a parenthesis 4e to the fourth plus 4 squared plus pi to the fifth. And then I have a matching parenthesis. These are really useful to have. Subtract 4e to the 0 plus 0 squared plus pi to the fifth. And 4 minus 0 is 4. Okay, so why is a parenthesis good to have? Well, if you have this minus, it helps remind you that it distributes through. Oftentimes people forget it, and they forget to distribute the minus through. So that's why parentheses are your friends. What happens with those pi to the fifths? They cancel. We'll talk about that in a second. What happens with e to the 0? Yeah, so that's 1. So what do we really have? Upstairs we have 4e to the fourth, 4 squared, 16 minus 4 over 4. Well, 16 minus 4 turns out to be 12. And then we have e to the fourth plus 3. Now, what do we do with this e to the fourth? We leave it as e to the fourth. So we are after exact answers. Can't be more exact than e to the fourth plus 3. Okay, so let's jump back. Why did the pi to the fifth not make any difference to our final answer? What is that pi to the fifth doing to the function? Okay, so that's an algebraic explanation. There's no x values, so they're canceling each other out. Is there a geometric explanation?
It just shifts the function up.
It's a shift. So if you think about what the function is doing, I don't know what it looks like, but let's say this is what it looks like. Well, if I add another number, it might shift it down if that number is negative, or it could shift it up if that number is positive. Like this, by the way, is our special effects. Wow. They can move the paper up and down. Math is amazing. How could they afford that on the budget? Well, but anyways, the moral is we're shifting up and down. But if you shift it up and down, it doesn't affect the slope through those points. So that's why geometrically, this number, if it's a constant, doesn't affect your average rate of change. And of course, someone said algebraically, they cancel out. All right, well, great. So we can do average rates of change. Nothing bad. Very good. No surprises. Life is good. But it's still somewhat unsatisfying. Okay. So what do we want to get to? Well, we want to get to the point where we have our function. Okay, so it's going up and down. And we might say, I want to know not what's happening everywhere. I want to know what's happening here. At this point, how is it changing at that moment in time? So that's called an instantaneous rate of change. And the hard part about this is spelling it. All right, so we have our instantaneous rate of change. What's happening at that moment? And that's where we want to get to. And we're not going to do it today because we're almost out of time. But I want to talk about sort of the intuition. You say, well, okay, what are we good at? What's the answer? We're good at lines, right? And that's a great answer. So we say, the problem is it doesn't look flat. But wait. What if we pull out our magnifying glass? Okay, let's do that. We pull out our magnifying glass. We zoom in. And we say, well, if you look closer, it's doing that. And we're after that point. It's better, but we could be even better. What do? We pull out our microscope. And we say, okay, if we zoom in, look closer, it's looking like that. It's now looking a little bit flatter. But can we do better? Well, we go over to the physics department. We use all their expensive machinery. They have a huge microscope. And we zoom in a lot. And what do we see? It looks something like that. And we channel our inner Frankenstein. And we say, it's a line! It's a line! Right? Anyways, the point is, it's flat. We like flat things. And now we have something that we can work with. Now the question is, how do we get to this flat thing? So, a flat thing and this is our happy place. And that's going to be a wonderful digression to how we do that. That's going to take us a while. And that's what we have to look forward to for the next 3 or 4 lectures. But before you go, we always are going to finish with a practice problem that involves multiple choice. Because we need to get good at doing multiple choice. So we have a few minutes left. Here's our problem for today. We're given the following information. The average rate of change of f of x from 3 to 7 is 5. The average rate of change of f of x from 5 to 7 is negative 3. The average rate of change of f of x from 5 to 15 is 7. Then, the average rate of change of f from 3 to 15 is it 3, 4, 6, 8, or 9? Now, let me point out, we know how students think. So we may have guessed some things you might have done. What are some things you think you might have tried? I think somebody might have tried to add the numbers. And then you may have guessed, 5 plus 7 minus 3 is what? Ooh, and 9 is there. That's very tempting. but it's not 9. And of course it's not 9 because you were supposed to average your averages. So you should have divided it by 3. And look, there's a 3 there. It's not 3. Does anybody know the answer? It's not 6, I heard somebody say. It's 8. Now you're like, what? How could it possibly be 8? Well, really quickly, what do we have? Average rate of change says we know f of 7 minus f of 3 divide by 7 minus 3, which is 4, is 5. Because that's the formula. Here's the average rate of change from 7 to 3. It is 5. You do it for the other ones as well. F of 7 minus f of 5 divided by 2 is negative 3. F of 15 subtract f of 5 divide by 10 is 7. Yes? All right. Now, we write down what we really have. F of 7 minus f of 3 is 20. So this is saying, right now, f of 7 minus f of 3 over 4 is your average rate of change. This is your difference. This is how much the function changed. We have f of 7, minus f of 5 is negative 6. F of 15 minus f of 5 is 70. If you subtract this one, add the others, what happens, the f of 7's cancel, the f of 5's cancel, you get f of 15 minus f of 3, 70 plus 20 minus negative 6 is 96. But wait, 96 isn't the answer. What do you need to do to get your average rate of change? Divide by 12. And 96 over 12 is 8.